In this video, we're going to be discussing expected value. Expected value is a mathematical way to use probabilities to determine what you should expect in various situations over the long run. Right, expected values are going to be used in several different situations, but they only give us a number that makes any sense over a large number of trials or a type of trial that's run repeatedly. The expected value, however, is used for a lot of different things in the real world, including determining premiums on insurance policies, weighing the risks and benefits in business decisions, and something else that I'll read in a second, indicating to a player in a game of chance what's likely to happen if the game is played repeatedly. So these are some of the situations you'll see expected value used in. It really is an important idea to understand that your book also calls expectation. Now, the standard way that we're going to compute these, well, let's actually see how we get to that by looking at an example. Let's suppose you were asked to survey 8,000 families with 3 children and then determine how many girls there were in those 8,000 families. So what would you expect would happen? To help us to kind of figure out what we would expect, or what you might expect, let's kind of look at the different kinds of families you can have. If I look at a tree diagram and I draw it out, I'm going to see that 8 different things can happen. You can have girl, 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 boy, girl, so on and so forth. And there's 8 different things that can happen. Typically, I will ask in class at this point about whether or not it matters what order you are in a family, whether you're the middle girl or the last girl. If any of you have ever had siblings, you know that's a huge difference in family order. So we are certainly going to call these 2 different things. All right, so I'm looking at all the possible outcomes of this experiment. I am going to say these are 8, and these are 2 different things. Now, each of these 8 outcomes is equally likely, but what I'm really concerned with here is the number of girls in these families. That was the question. So I can have 3 girls, 2, 2, 1, 2, 1, 1, 0. When I count these up, of those 8, I get 3 one time. I get 2 3 times, 3 of those 8 times. I get 1 girl 3 of the 8 times. And I get 0 girls 1 of the 8 times. Well, if I'm doing this 8,000 times, I'm expecting 3 girls, 1 out of every 8, probably 1,000 times. I'm expecting 2 girls. This happens 3 out of every 8 times on average. 3,000 times. 1 girl, well, 3 out of 8, 3,000 times. And 0 girls 1,000 times. So I should get, from the 3 girl families, I should get about 3,000 total girls. From the 2 girl families, I should get about 6,000 total girls. From the 1 girl families, I should get about 3,000 total girls. And from the 0 girl families, I should get 0 girls. Looking at that, 3,000 plus 6,000 plus 3,000, I should expect to get about 12,000 girls or so if I surveyed 8,000 families with 3 girls each. Now, the question I would really want to ask when I'm talking about expected value is I want to look at, on average, for one of those 3-child families, how many girls did they have? Well, there were 12,000 girls total, and there were 8,000 families. So on average, 12,000 girls, 8,000 families. I'm thinking that on average, take the 12,000 total girls, divided by 8,000, you should have 1.5 girls in a 3-child family, on average. Which is probably what you expect to see. You should have half of the people in the family be girls. This is not horribly surprising, I expect. But there's an easier way to do this. I didn't really have to think about it being with 8,000 families, though that makes it easier for some of us to see what's going on. There's another way to do this. What we did here was our overall, I divided this amount by 8,000, which was the same as dividing each of these amounts by 8,000, which is actually the same as dividing each of these amounts by 8,000. And if I do that, let me look at a couple of these. So skipping out some of these steps. Well, 1,000 divided by 8,000 is 1/8. 3,000 divided by 8,000 is 3/8. 3,000 divided by 3/8 is 3/8. 1,000 divided by 8,000 would be 1/8. Those look a lot like these numbers that were right here. It's because they are like the same number in all. And I multiplied those numbers out and added them up, and that's exactly the process we'll use. The expected value in this case would be 3 times 1/8 plus 2 times 3/8 plus 1 times 3/8 plus more 0 times 1/8. If I add all this up, I'm going to get 1.5. And this is the process I will usually use. I'm going to take the number times its associated probability, add that to the next number times its associated probability, add that to the next number times its associated probability, and just keep doing that for all the numbers and probabilities I have to give me the expected value. Very important in any discussion of the expected value is what exactly this means. Now going back to the 8-child family, what it gets at is that the best number I can see for the average number of girls I would expect in a 3-child family, if I look at lots and lots and lots of 3-child family, is 1.5 girls. It's the long run average. Alright, so in our example, we're thinking about having lots and lots of families. Expected value also works if I look at one event that I'm repeating. So for instance, let's say I flip a coin 3 times, which is exactly the same setup for this. If I flip a coin 3 times, on average I should expect to get 1.5 heads. I think we've seen something similar to this before. On average I would expect to get 1.5 heads. Well, I can flip 3 coins, record my results. I can flip 3 coins, record my results. If I do this 10,000 times, if I do this trial repeatedly, I should expect the same thing. Alternatively, I could take 1,000 people and all have them flip a coin 3 times, and I would expect the same results for an expected value. The idea works the same in both instances.